For today's video, we're going to use what we learned yesterday and we're going to build on it. Yesterday we looked at inequalities and today we're going to look at compound inequalities. So a compound inequality is when we take two simple inequalities and we combine them into one statement using words like and or, and we call that a compound inequality. So just like we did before, we can also represent the solutions to these on graphs. When we have an and inequality, we're going to look for an overlapping region between our two different inequalities. And that overlapping region can be called the intersection, and it's going to show numbers that are solutions for both inequalities. So in this example, we have two simple inequalities. So we have x is less than 10. So they showed that right here. They started at 10 and went to the left for less than. This one says x is greater than 0. So they started at 0 and went greater. If we want a compound inequality that's going to have either words or multiple inequality signs, we're trying to show between 0 and 10, and we can indicate that on our number line. So first two examples we'll look at actually do use the word and. So we see x plus 1 is greater than negative 5, and x plus 1 is less than 2. So when they're split like this, I typically just solve them as two separate inequalities, and then I'll handle graphing. So on that left side, the x plus 1 is, let me zoom in a little bit more, is greater than negative 5. We're going to solve that just like we learned how to yesterday. So to get x by itself, we would need to subtract 1 on both sides, which gives us x is greater than negative 6. So there's part of my inequality. I need to deal with the other one as well. That one said x plus 1 is less than 2. So to get that x by itself, I would need to subtract 1 on both sides, and we get x is less than 1. So what I have here are two different answers. I know that x has to be greater than negative 6 and less than 1. It has to meet both requirements. So essentially what we're saying is that if it has to be greater than negative 6 but less than 1, we're going to be in between negative 6 and 1. On my number line, I need to make sure that I see both of those numbers. So I'm just going to start down here at negative 6. I'm going to count up until I get to negative 1. Or sorry, to positive 1. And so let's think about the x is greater than negative 6 first. Based on what we learned yesterday, for that one, we would put an open circle at negative 6, and greater than would go to the right. I'm going to kind of pause that line partway through so we can figure out where to stop. For my second inequality, it says x is less than 1. So I would put a open circle at 1 and go less than, and so the section that I'm interested in is where these two would overlap or run into each other. In that space are all of the possible options that meet both requirements, numbers that are greater than negative 6 and less than 1. All right, for example B, our inequality gets a little bit more difficult, still just a two-step though. So again, I'm going to solve them both. Got 3x minus 1 is greater than 8. So I would add 1 on both sides, just like a two-step equation, which means 3x is greater than 9, and then divide by 3. So one part of my solution is that x must be greater than 3. We can't stop there though, because we have this and statement. We have a whole nother inequality we need to deal with. So we have 3x minus 1 is less than or equal to 11. So to get that by itself, we're going to follow the same steps. We'll add 1 on both sides. We get 3x is less than or equal to 12. Divide by 3. Divide by 3. We would get x is less than or equal to 4. So what I see here is I need numbers that are greater than 3, but also less than or equal to 4. So they have to be in the overlapping section. So this one actually spanned much of my number line. I'm going to put 3 and 4 right in the middle. So for greater than 3, I would put an open circle and go this way. to the right for greater. For less than or equal to 4, that would be a closed circle at 4 that goes the other way. So only numbers more than 3, but less than or equal to 4 would work. So a couple things to think about here. 3 does not work here. 3 is not greater than 3. 3.5, for example, works. 4 works because we are allowed to be equal to 4 because of that equal to piece in our inequality. Now, there's another way that we can also write these without using the actual word and so check out example C. We've got 2 symbols, and it's all just kind of embedded into one. I like to do the least writing possible, so you could split these up if you wanted to. If I'm going to do this, I'm going to show you kind of a shortcut. I'm going to imagine I'm trying to get that x in the middle by itself. So if I want that x to get by itself, I want to leave the x in the middle, and I want to get just numbers on either side. I would add 10 to get rid of it. If I do it there, I've got to do it on this side and this side, on both sides of my inequality. And again, you could split this up, but this allows you to do a little bit less writing, which I think is nice. So -9 plus 10 is 1. The x should now be by itself. -5 plus 10 would be +5. And I like this, I like the way this is written because it makes it very clear x needs to be in between 1 and 5. I think this notation really lends itself to understanding that. So on my number line, I'm going to put 1, 2, 3, 4, 5. Now imagine both of these will need to be open circles because they did not include the equal to part. And we wanted those numbers in between. So these are numbers that are greater than 1, but are less than 5, all right in there. All right, we can do the same thing even if it gets a tiny bit more complicated. So in that next one, we've got -4 is less than or equal to 3n plus 5, which is less than 11. So if I'm trying to get that n by itself again, which is our goal, I don't want to move it from the middle. We want to keep the n right in the middle. This is a 2-step, so I would move the 5 first because it's added, so I would subtract 5 on both sides. That would give me -4 minus 5 is -9, is less than or equal to 3n, is less than 11 minus 5 is 6. And then final step would be to divide by 3. And that means everything gets divided by 3. So -3 is less than or equal to n is less than 2. So again, I like this representation because I know my n values have to be right in between -3 and 2. Makes it very clear. So we'll start with -3 and count all the way up to 2. And you can certainly put more numbers. I just think those are going to be our most important ones. So at -3 this time we should have a closed circle, which will go this way. 2 would be an open circle. And remember, to decide that, we're paying attention to, does it have the equal to line or not? So we want numbers in between -3 and 2. -3 is included, but 2 is not. All right, so those are and examples. There are also what we call or compound inequalities. So when you have an inequality involving the word or, what we're really looking for instead of an intersection is a union. So or, you're going to have 2 separate sections that could both work because we're allowed to keep the values as long as they meet just one of the requirements. And they had to overlap or they do not. So in this example, they've got x is less than 0, so that would be right there going that way. X is greater than 10 would be going this way. If we put that or in the middle, we can have the less than 0 part or the greater than 10 part. So we have 2 different sections to our number line. So we'll solve these just like we did before. With the or ones, they will have the word in there for you. So I've got 8 plus t is greater than or equal to 7. So to get that t by itself, I would subtract 8 on both sides. So we get t is greater than or equal to 7 minus 8 is -1. So there's my first part. I also have 8 plus t is less than 2. I would subtract 8 on both sides and get t is less than -6. So So there's my two pieces, and this was an or problem. So I want to definitely go from -6 at least to -1. So let's start with the greater than or equal to -1. At -1, we're going to have a closed circle. And if I want greater than, that would be going to the right. So we're going this way. For t is less than -6, we would have an open circle at -6. And we'd be going to the left because we want less than. And again, because this was an OR problem, we can have those two separate sections. It's called a union of those two pieces that make up our solution. All right, example B, same idea, but we've got two-step equations this time, or two-step inequalities, excuse me. So 4x plus 1 is less than or equal to 21. We would subtract 1 on both sides. We get 4x is less than or equal to 20. And then divide by 4. Got ahead of myself. Divide by 4. We get x is less than or equal to 5. So there's the first part of my union. We've got to find the second part. For the 3x minus 2 is greater than 19. So I would add 2 on both sides. We get 3x is greater than 21. Divide by 3, divide by 3, and we get x must be greater than 7. So there's the second part of my union. So I really only need to go from 5 to 7 here. If we say x is less than or equal to 5, we'd have a closed circle at 5, and less than would go to the left. If we have a greater than 7, we would put an open circle at 7 and go to the right. So this union has most numbers, actually, other than right up to 5. So 5 is not included, but right up to 5, and then to 7, just excluding a few numbers there.